Hey there, science fans! Welcome back to another exciting episode where we explore the wonders of the scientific world. Today we're diving into the fascinating world of units and measurements. These are the building blocks of science, the tools that allow us to make sense of everything from the tiniest particles to the vastness of the cosmos. You might be thinking, units and measurements? Sounds kind of boring, but hold on, because once you understand their importance, you'll see how they impact every aspect of our lives. But trust me, this stuff is crucial to understanding the universe around us. Without units and measurements, we wouldn't be able to conduct experiments, build technology, or even cook a meal properly. Imagine trying to bake a cake without any measuring cups or spoons. You'd have no idea how much of each ingredient to use. How much flour would you use? A handful? A bucketful? The results would be unpredictable and probably inedible. Without standardized units of measurement, things would be total chaos. Your kitchen would be a disaster zone and your cake would be a flop. The same goes for physics. Scientists rely on precise measurements to test theories and understand natural phenomena. Whether we're talking about the tiniest atom or the vast expanse of space, units and measurements allow us to quantify and compare the physical world. They help us grasp the scale of the universe and the intricacies of atomic structures. They're the language of science, helping us communicate our observations and discoveries with precision and accuracy. Without them, scientific progress would be impossible. Think about it. How would you describe the size of your bedroom without using units like feet or meters? You'd be left with vague descriptions that don't convey the true dimensions. It would be pretty tough. You'd struggle to explain it accurately to someone else. You might say it's big or small, but those terms are relative and open to interpretation. What's big to one person might be small to another. Units give us a common language to describe the world in a way that everyone can understand. They bring clarity and consistency, making it possible for us to share knowledge and build upon each other's work. Now let's talk about the fundamental units. These units are the cornerstone of all scientific measurements and are essential for understanding the world around us. These are the basic building blocks of all measurements. Without them, we wouldn't be able to quantify or compare anything accurately. Think of them like the prime numbers of the measurement world. Just as prime numbers are the building blocks of all whole numbers, these fundamental units are the building blocks of all measurements. Just like you can build any whole number by combining prime numbers, you can derive countless other units from these fundamental ones. So, what are they? Let's dive into the 7 fundamental units that form the basis of the International System of Units. In the International System of Units, SI, which is the most widely used system of measurement in the world, we have 7 fundamental units. These units are meticulously defined and universally accepted, ensuring consistency and accuracy in scientific research and everyday life. Meter, M, used to measure length or the distance between 2 points. Whether it's the height of a building or the width of a river, the meter helps us understand spatial dimensions. Kilogram, kg, used to measure mass or the amount of matter in an object. From weighing groceries to calculating the mass of celestial bodies, the kilogram is indispensable. Second, S, used to measure time or the duration of an event. Time is a fundamental aspect of our lives, and the second is the unit that helps us keep track of it. Ampere, A, used to measure electric current or the flow of electric charge. From powering our homes to running complex machinery, the ampere is crucial in the world of electricity. Kelvin, K, used to measure temperature or the degree of hotness or coldness of an object. Whether it's the weather forecast or scientific experiments, the Kelvin is key to understanding temperature. Mole, mol, used to measure the amount of substance or the number of elementary entities, like atoms or molecules, in a sample. This unit is fundamental in chemistry and helps us understand the composition of matter. Candela, CD, used to measure luminous intensity, or the amount of light emitted in a particular direction. From the brightness of a flashlight to the intensity of streetlights, the candela helps us quantify light. Can you think of an example of how we use the fundamental unit of time, the second, in everyday life? It's more common than you might think. We use seconds to time everything from races to cooking to how long we brush our teeth. These fundamental units are not just abstract concepts, they are integral to our daily routines and scientific endeavors. Now that we've covered the fundamental units, let's move on to derived units. These units are formed by combining the fundamental units in various ways. They're like the compound words of the measurement world, built by combining simpler units to describe more complex concepts. For example, speed is a derived unit because it's calculated by dividing distance, meter, by time, second, giving us meters per second, m/s. Similarly, volume, which measures the amount of space an object occupies, is derived from the fundamental unit of length, meter. We'll delve deeper into volume in a later section. Can you guess the derived unit for acceleration, which is the rate of change of velocity over time? If you said meters per second squared, mms2, you're right. Acceleration is calculated by dividing the change in velocity, meters per second, by the time it takes for that change to occur, second. Length is the most basic of all measurements. It's the distance between 2 points. We use length to measure everything from the size of our shoes to the distance between cities. The SI unit of length is the meter m, but we also use other units of length, depending on what we're measuring. For example, we use centimeters, cm, to measure the length of a pencil and kilometers, km, to measure the distance between 2 cities. To calculate the length of an object, we can use a ruler, a measuring tape, or even more sophisticated instruments like laser rangefinders. If you run 1,000 meters, how many kilometers have you run? You've run 1 kilometer. Remember, there are 1,000 meters in a kilometer. Section 5. Measuring volume. How much space does it take up? Volume is the amount of space a three-dimensional object occupies. Think of it as the amount of stuff an object can hold. We use volume to measure everything from the amount of liquid in a glass to the size of a building. The SI unit of volume is the cubic meter, or m3. However, we often use liters and milliliters to measure the volume of liquids. To calculate the volume of a regular-shaped object like a cube or a rectangular box, we can use the formula volume equals length times width times height. So here's a question. What's the volume of a cube with sides of 5 centimeters each? The answer is, the volume is 125 cubic centimeters. 5 centimeters times 5 centimeters times 5 centimeters equals 125 cubic centimeters. Section 6. Mass versus weight. Not quite the same thing. People often use the terms mass and weight interchangeably, but they're not the same thing. This common misconception can lead to confusion, especially in scientific contexts where precision is key. Mass is the amount of matter in an object. It's a measure of how much stuff an object contains, and it's a fundamental property that doesn't change. It's a fundamental property of an object, and doesn't change no matter where the object is in the universe. Whether you're on Earth, the moon, or floating in the vacuum of space, your mass remains constant. Weight, on the other hand, is the force exerted on an object due to gravity. This means that weight can change depending on where you are. Weight depends on both the object's mass and the strength of the gravitational field it's in. For example, an object will weigh less on the moon than on Earth because the moon's gravitational pull is weaker. The SI unit of mass is the kilogram, while the SI unit of weight is the newton. This distinction is crucial for scientific measurements and calculations. If an astronaut weighs 180 pounds on Earth, how much would they weigh on the moon, where the gravity is about 1/6 that of Earth's? This is a fascinating way to understand the difference between mass and weight. They would weigh about 30 pounds on the moon. This dramatic difference highlights how weight is influenced by gravitational forces. Their mass would remain the same, but their weight would be less due to the weaker gravitational pull. Understanding this distinction is essential for fields ranging from physics to engineering. Section 7. Keeping time. The ever-ticking clock. Time is another fundamental concept in physics. It's what prevents everything from happening all at once. We experience time as a continuous flow, always moving from the past to the present to the future. The SI unit of time is the second, but we also use other units of time like minutes, hours, days, and years to measure longer durations. We use clocks and watches to measure time. Atomic clocks are the most accurate timekeeping devices ever invented, losing less than 1 second every 100 million years. How many seconds are there in an hour? There are 3,600 seconds in an hour. 60 seconds in a minute times 60 minutes in an hour equals 3,600 seconds. Section 8. Units and measurements in action real-world applications. Units and measurements are everywhere in our daily lives. From checking the speedometer on your car to measuring ingredients for a recipe, we rely on units and measurements constantly. Engineers use units and measurements to design bridges, buildings, and other structures. Doctors use them to prescribe the correct dosage of medication. Scientists use them to conduct experiments and analyze data. Think about it. How do units and measurements play a role in your favorite sport or hobby? Whether it's timing a race, measuring the distance of a golf shot, or calculating the weight limit on a fishing line, units and measurements are essential for fair play and accurate record keeping. Section 9. Conclusion: Units and Measurements. The universal language of science. So, there you have it, folks. Units and measurements are the unsung heroes of the science world, providing us with a common language to describe and quantify the universe around us. From the tiniest subatomic particles to the largest galaxies, units and measurements allow us to make sense of the world and communicate our discoveries with clarity and precision. So the next time you're measuring ingredients for a batch of cookies or checking the distance on a map, remember the importance of units and measurements. They're not just numbers and symbols. They're the key to unlocking the secrets of the universe. Stay curious, keep exploring, and never stop asking questions.